for all of you for coming back to hear the second lecture. So let's remember where we were at the end of the first lecture. So we had introduced the von Neumann entropy of a density matrix rho, which is defined as minus trace of rho log rho. And I had explained its analogy with entropy in classical mechanics. I also explained Raphael Sorkin's suggestion that in the generalized second law of Bekenstein, the entropy outside the black hole should really be defined as the von Neumann entropy of the density matrix for observations outside the horizon. The general picture is that we divide space into two regions A and B, and we consider a density matrix in, let's say, region A, appropriate for measurements only in that region. And formally, it would have a von Neumann entropy, and Sorkin said that should be the S out. And then I explained one more fact, which was the observation of Susskind and Uglum, that if we interpret S out this way, the generalized entropy is better defined than either term on the right-hand side is separately. So as Sorkin had noted, S out has a quadratic, a divergence proportional to the area of the horizon. In 4 dimensions, it's a quadratic divergence. And it's slightly less obvious, but the area term also is divergent. I don't feel I explained it well, so I want to go over that for a second. The problem is that there's an ultraviolet divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. At one loop order, the relation is that 1 over GH bar is 1 over G naught H bar plus a constant times the square of an ultraviolet cutoff. And the form of the divergence is exactly the same as the form of the divergence in S out. They're both independent of H bar in one loop order. And Susskind and Uglum showed that they have equal and opposite coefficients. Now later authors improved on this, but Susskind and Uglum showed that it was true at one loop level. So possibly that's the most elementary reason that the von Neumann entropy is the right interpretation of S out. It simply makes the formula make sense, which it does not otherwise. Or at least it makes less sense otherwise. It helps that the formula makes sense quantum mechanically. But I will be, today and tomorrow, be giving other reasons that this interpretation for S out has to be the correct one. So my goal today and tomorrow is to explain modern developments that depend on understanding a microscopic definition of entropy, and especially depend on using the von Neumann entropy as what we mean by entropy. So I'm going to start with one of the striking early developments, arguably the first, well, almost, well, anyway, one of the striking early developments, which was Horacio Cassini's interpretation and proof of the Bekenstein bound. So first I want to review what is the Bekenstein bound. So in 1980, Bekenstein went back to the same subject matter he'd considered in his original paper 8 years earlier. He asked if the generalized second law is obeyed when a black hole of mass m and therefore radius 2gm, I'll assume a short-shield black hole, absorbs a body of size curly r, energy E, and entropy S. The entropy S of the body disappears, so the generalized second law says the increase in the black hole entropy must be more than that. The black hole entropy changes because when the black hole mass increases by E, its area goes up. And we actually computed Monday my time, Tuesday your time, that the black hole entropy changes by 8 pi g me, where m is the mass of the hole and E is the energy of the body it absorbs. So for the Bekenstein bound, we want 8 pi g me to be bigger than S. Well, if one naively says that a black hole of size 2gm, a black hole of mass m, has radius 2gm, if we say it can only absorb a body of size r, if curly r is less than 2gm, then the desired inequality can be written in terms of the size of the body that's being absorbed, curly r, the energy of the body being absorbed, and also the entropy. And when you write it that way, Newton's constant disappears. So the formula makes no mention of gravity or Newton's constant. So it's potentially just a statement about ordinary quantum physics without gravity. Now, my explanation didn't do justice to Bekenstein's argument. He considered a highly rotating black hole, and he tried to give a more convincing explanation with better constants. But we're not going to go into that. And for us, we'll take the Bekenstein bound to be the statement that there's some universal constant K, so that in quantum field theory without gravity, the size, energy, and entropy of any system obey this universal bound, which says that size times energy is bigger than a constant times the entropy. So for us today, that will be what the Bekenstein bound means, and we'll discuss whether it's correct. Well, if you're given a conjecture like this, there are two questions that come to mind. One question is certainly whether it's true, but an equally important question is whether it's interesting. Now, for years, there seemed to be lots of reason to be skeptical on both counts. So on the question of whether the Bekenstein bound was true, there seemed to be a trivial argument it could not be true. At least it could not be a universal statement about all quantum field theories. Consider a theory that has n elementary particles all of the same mass. Such theories exist, for example, free field theories. Consider a system consisting of a box with one particle inside the box. The entropy seems to be at least log m from the choice of one of n particles to put in the box. On the other hand, the size and energy of the box do not depend on n. So it seemed clear that the Bekenstein bound could not be a universal statement about quantum field theory. So for example, I thought this argument was convincing, and I thought maybe the Bekenstein bound is supposed to be true in the real world, but not in arbitrary quantum field theories. But as I'll explain, that turned out to be the wrong interpretation. On the other hand, if true, is the Bekenstein bound interesting? Can we think of a system where it's close to being violated? Or is it such a weak bound that it never really says anything that isn't obvious? Consider a system made of massless particles. Well, if the particles are massive, that increases the energy without increasing the entropy, so it goes in the wrong direction. It makes the Bekenstein bound more trivial. But suppose we have massless particles. For example, consider a box of size rho that contains a gas of massless particles at temperature T. In 3 dimensions, the number of particles in the box is of order rho T cubed, and the entropy is of the same order. S is rho T cubed times a dimensionless number, which depends on how many particle types there are. On the other hand, the energy is rho cubed T to the 4th, again times a universal constant that doesn't depend on rho or T. So the Bekenstein ratio S over rho E, on which we want an upper bound, is of order 1 over rho T. Now, if rho T is much bigger than 1, the notion of a thermal gas in a box makes sense. But in that case, S over rho T is much smaller than 1, and the bound on S over rho E provided by the Bekenstein bound is not interesting. S over rho E is trivially smaller than Bekenstein's bound, much smaller. Well, can we make the Bekenstein bound more interesting by considering something else? Well, still with many particles in the box, but assuming the particles aren't in thermal equilibrium, makes matters worse, because it lowers the entropy S for given energy E. Thermal equilibrium maximizes the entropy for given energy. To make the Bekenstein bound challenging, we need to reduce the number of particles, which we can do by lowering the temperature. The best case is that the box contains just one or a few massless particles, or equivalently that the temperature is no more than 1 over the size of the box, which I guess I called rho on the previous page. But a box containing one or a few massless particles is going to weigh much more than the particles it contains. So in estimating the Bekenstein ratio, we can't ignore the mass of the box, which maybe we could ignore when there were many particles in the box. But if the box is almost empty, we certainly can't ignore the mass of the box. Including the mass of the box goes in the wrong direction and makes the Bekenstein bound uninteresting. So, in other words, the case that the Bekenstein bound is interesting is the case of a single particle without a box. But what sense does the Bekenstein bound make in that case? In other words, what's the entropy of a single particle? For that matter, what's the size of a system consisting of a single particle? that's not terribly well defined in quantum mechanics either. In other words, when we try to go to a regime in which the Bekenstein bound is interesting, the statement of the Bekenstein bound does not seem to make sense. But one thing that may be clear from all this is that to make the Bekenstein bound interesting, we need to define entropy in such a way that it makes sense to talk about the entropy of a single particle. In other words, we need a microscopic notion of entropy that makes sense even when thermodynamics does not apply. Now, as I've been telling you, the von Neumann entropy has that property. So not surprisingly, that's, well, with 2020 hindsight, it's not surprising that that's what we're going to need. So amazingly, Cassini was able to give a precise definition to the terms in the Bekenstein bound and to prove it. To explain this, I need to tell you one more thing about density matrices. Let sigma and rho be two density matrices on the same Hilbert space H. The relative entropy between them is defined by this formula, the trace of rho log rho minus rho log sigma. Now, if I had more time, but it really would take at least half a lecture, I try to explain what motivated that definition. But for today, we're only going to need one or two facts about it, of which the one we need for Cassini's result, I'll kind of sketch a proof on this page. So the relative entropy measures, in a sense that turns out to be useful, how different are rho and sigma. But for the Cassini work, all we care is this. Well, first of all, S of rho and sigma is obviously 0 if rho equals sigma. But the important point is that in general, it's non-negative, and it's strictly positive unless rho equals sigma. It vanishes if and only if rho is sigma, and otherwise it's positive. I'll very briefly sketch a proof. So a density matrix is a positive Hermitian matrix of trace 1, and the space of such matrices is convex. You can take linear combinations with positive coefficients that add up to 1, and you'll still have a density matrix. So in particular, let T be a real number between 0 and 1, and let sigma of T be a linear combination of rho and sigma with coefficients that add to 1. So sigma of T, or as I abbreviated here, sigma sub T, is a density matrix because it's a Hermitian matrix that's positive and its trace is 1. So therefore, we can consider the relative entropy between rho and sigma T by this formula. And it has the following properties. First of all, at T equals 0, sigma equals rho, and therefore f of 0 is 0. But it's also true that f prime of 0 is 0, and that f double prime of T is positive for all T between 0 and 1. Now, it's a short calculation to prove those statements. I'm not going to actually do it. I recommend the exercise. If you want to prove it for yourself, it'll help to use this formula for log sigma of T. See, the reason it's not completely trivial is that sigma and rho don't commute. So when you differentiate sigma of T with respect to T, you're dealing with non-commuting matrices. If you use this formula for the logarithm, you'll find that it'll be easier to calculate the derivatives you need. And then you can prove the statements in this sentence. I won't do that calculation, but I do recommend the exercise. Now, given the facts in this line, you see it follows that f is positive for all T between 0 and 1, except it vanishes at T equals 0. So in particular, f of 1 is positive, but f of 1 is the relative entropy between rho and sigma. So that's the statement that the relative entropy is positive whenever rho and sigma are different. Now, Cassini considered two states, the vacuum state of a quantum field theory and any other state psi. His goal is to interpret and prove the Bekenstein bound for psi. So psi is the state he's really going to study, but he's going to study it using known properties of the vacuum. So the goal is to prove the Bekenstein bound for psi with the correct interpretation of the terms. So first, Cassini divided space into the two halves, positive x and negative x, where x is one of the spatial coordinates. So I'll draw a two-dimensional picture with only x and t. So t runs vertically, x runs horizontally. If I made a slice at time 0, that would just be the division of the real line into two half lines that we studied 2 days ago. But a little bit differently. The domain of dependence, it's called, of the right half line is this wedge labeled A. The domain of dependence of the other half line is the wedge labeled B. Those are called Rindler wedges. So Cassini considered the density matrices of the state psi and omega, the vacuum state omega and some other state psi, reduced to region A. That means when one only considers measurements in region A. The way I said the same thing 2 days ago was I considered an initial value surface, because operators can always be, by solving the Heisenberg equations of motion, expressed in terms of operators at time 0. And therefore, instead of talking about measurements in the whole Rindler wedge, we could talk about measurements at time 0 in that wedge, which is the way I expressed the thought 2 days ago. But because of Lorentz invariant, Lorentz causality, it doesn't matter if you consider an initial value surface in the wedge A or the whole wedge. So the relative entropy between these states determines how well psi and omega can be distinguished by someone who only makes measurements in region A. But the only property we're going to use is that it's positive. Now, for brevity, I'll use here the language of density matrices, though a rigorous formulation can be made using von Neumann algebras. So we're going to compute the relative entropy. Here's its definition. It has as you'll see, it has the property that it's finite in quantum field theory, but actually it's written here as a difference of two terms that are both infinite. It turns out that either of these two terms has an ultraviolet divergence. So Cassini's first step is to add and subtract something to write the relative entropy as a sum of two terms that are both finite, ultra well-defined. So he added and subtracts trace of sigma log sigma. And as you'll see, the two terms in parentheses are both finite. Now, the first term is minus the difference of entanglement entropies between the state psi and the vacuum omega in the region A, in the Rindler wedge. So it's, since the entropy is minus trace of sigma log sigma, that would be S omega, and this one is minus S psi. The two terms here are simply the entropy of the state omega or psi for measurements in region A, in the Rindler wedge. Now, as we discussed last time, entanglement entropy, when you divide space in two pieces, has an ultraviolet divergence near the boundary. But that divergence is universal, independent of the state, because every state looks like the vacuum at short distances. So when we make this subtraction, it becomes finite. And this we'll call minus delta S. It's minus the difference of entanglement entropies between the state psi and the vacuum state omega. So the area law divergence has canceled out because we took this difference. Now let's discuss the other term, which is trace sigma log sigma minus trace rho log sigma. Now we remember that if O is any operator, then its expectation value in the vacuum, I should say if O is any operator in the Rindler wedge. For any operator in the Rindler wedge, its expectation value in the vacuum is the same as the trace of sigma times O, where sigma is the density matrix of the vacuum in the Rindler wedge. Likewise, the expectation value of chi, of O in the state chi, there shouldn't be a trace. Two typos in the sentence. The simple trace should not be there on the left. This is just the matrix element of O, the expectation value of O in the state chi. Assuming O only acts in the Rindler wedge, it's the trace of O times the density matrix of the Rindler wedge. And likewise for this one. So if I take O to be minus log sigma, the two terms here are the expectation value of O in the vacuum or in the state chi. But remember last time we showed that the density matrix of the vacuum in the Rindler wedge, or as I said it last time, in the half line, is the exponential of minus 2 pi times what I called k, which I've defined in a moment. So minus log sigma is 2 pi k, or in other words, 2 pi times the integral times the Lorentz boost generator, but only integrated over half of space, only integrated for positive x. I left the limits of integration off here, but I've put them in the next equation. So this formula is more precise. X is integrated from 0 to infinity, but the normal coordinates, which I ignored when I was deducing this formula last time, are integrated from minus infinity to plus infinity. What's integrated from x to infinity is only, from 0 to infinity is only x. So in other words, this is a partial boost generator. We define the Lorentz boost generator as an integral over time 0, but we're only interested in the part in the Rindler wedge. That's what we learned when we discussed the density matrix of the vacuum for a half line. So anyway, this is minus log sigma. So the second term in our formula, that is this one, or this one, sorry, which is the same as trace sigma O minus trace rho O, with O being minus log sigma and sigma minus log sigma being 2 pi k. The second term is just 2 pi times the matrix element of k in the state psi minus the same thing in the vacuum state. So explicitly, that's 2 pi times an integral over half of space at time 0. X goes from 0 to infinity. The normal coordinates are integrated from minus infinity to infinity. Now I should, in principle, subtract the same thing for the vacuum, but with usual normalization, regularization of t00, its vacuum expectation value vanishes. So the term we subtract is 0. The effect of making the subtraction is that the regularization doesn't matter. If I write this formula without the vacuum subtraction, I have to tell you that t00 is defined to be 0 in the vacuum. But Cassini's derivation naturally leads to the difference between this integral in the state psi and the same integral in the vacuum. So in that difference, the ultraviolet divergence in the energy density also cancels. So let's define curly E to be this integral. Okay, now I finally wrote that the normal coordinates are integrated from minus infinity to infinity, but x is only integrated from 0 to infinity. So curly E is the integral at time 0 over half of space of x times t00 in the state psi. Cassini had the following insight. Suppose psi is a quantum state that describes a system that intuitively is localized almost entirely in the region A, which is where x is positive, and then has size r and energy E. Then this integral curly E is at least E times r in order of magnitude, up to a factor of order 1. That depends on exactly what you meant by localized almost entirely and so on. So Cassini's idea was that the heuristic ER of Bekenstein should be replaced by curly E. So see, if a system has energy E and is located at x equals A, let's say, this integral is approximately E times A. But it's defined for all states, even if you don't have a semi-classical picture. So this expression in particular is defined for a single particle that's partly in, partly out, the region of positive x. Whatever the state is, the integral is defined. Cassini also proposed that delta S, the difference in entanglement entropies of the Rindler wedge between the state psi and the vacuum state omega, should replace the heuristic S in the Bekenstein proposal. The positivity of relative entropy says that curly E is bigger than the entropy difference over 2 pi, with equality only if psi is the vacuum. So that is Cassini's rigorous version of the Bekenstein bound, valid for all quantum states. And you see, you might have thought it was too optimistic to have a universal Bekenstein bound. There is one, but to have it, we needed we couldn't interpret entropy as thermodynamic entropy. We needed a microscopic definition of entropy that made sense in general. So I think it's an important result because it's, I think, well, by some yardsticks at least, the first one where a traditional confusion deriving from black hole thermodynamics was resolved by using a clear definition of what you mean by entropy. Now, maybe this is a reasonable time for questions if there are some. I hope if there aren't questions, it's more because everybody's happy with what I said and not because I've confused you all.
Sorry, can I ask a brief question before?
Sure, yes.
There was some previous work by Marolf.
Yes.
But since I'm not that familiar with that, was it too different from what Cassini proposed? More precisely, because Cassini, I think, then really defined how the state should be localized, right? So,
well, I'd say he defined exactly what you mean by E times R and what you mean by S.
okay.
The state is a completely arbitrary state, but he gave the right definitions of E times R and also of S. I don't fully know Meyerhoff's work, but one sense in which Meyerhoff was getting close was that he understood that when you try to violate the Bekenstein bound, quantum fluctuations in the vacuum become very important, and intuition can break down. And that's actually true here, because if you ask what's wrong with trying to violate the Bekenstein bound with n species for very large n, well, there are quantum fluctuations that pairs appear in the vacuum. And if you observe just one Rindler wedge, you might accidentally find a particle there that is there by accident as a vacuum fluctuation. Its partner is in the other Rindler wedge. And that confuses. We applied semi-classical reasoning in a way that isn't really valid when we claimed that the entropy of one particle in the box was at least log n for n species. So although I do not feel I fully understand the history, it is true that in Meyerhoff's papers of this period, he was considering issues involving the breakdown of classical reasoning when quantum fluctuations become large for such reasons.
Thank you.
Sure. Any other question on what I've said so far? If there isn't, I think I'll go on. But before getting on to the next topic, which will be the generalized second law, I'm going to make a few more general remarks comparing the von Neumann entropy to thermodynamic entropy. So thermodynamic entropy is a notion that makes sense for systems close enough to equilibrium, or at least locally close enough to equilibrium, in a sense we'll discuss in a moment. It compares with the von Neumann entropy, which is universally defined. So for any system in any state, we can define the von Neumann entropy. We can define the thermodynamic entropy if you're close enough to equilibrium. If a statement is, I'll clarify that in a moment. If a system is truly in thermal equilibrium, that means its density matrix is a thermal density matrix. There should not be the trace here, sorry. Pretend I haven't written trace. The thermal density matrix is e to the minus beta h divided by a constant that's chosen so that the trace of rho is 1. So if rho is a thermal density matrix, then the von Neumann entropy equals the usual thermodynamic entropy as thermal. But the von Neumann entropy is always defined whether a system is in thermal equilibrium or not. When we say a system is thermalized, we don't normally mean literally its density matrix is rho thermal, which is very hard to achieve for a macroscopic system. We mean that simple accessible measurements don't distinguish rho from rho thermal. In such a system, the microscopic von Neumann entropy is less than the thermal entropy, possibly much less. It can never be more because the thermal entropy is the entropy, well, the density matrix that maximizes the entropy for given energy is the thermal density matrix. So any other density matrix of the same energy has less entropy. And since the energy is one of the things you can measure by a simple measurement, that means any non-thermal state that you can't distinguish from thermal equilibrium by simple measurement has strictly smaller entropy. So usually when we say a system is thermalized, its density matrix isn't really row thermal. It just isn't easily distinguished from row thermal. The thermal entropy is what you get if you coarse grain and approximate the actual row as row thermal. So a basic difference between the two kinds of entropy concerns the second law. Consider an isolated system, say a fluid in a box, initially in an inhomogeneous state, but with local equilibrium. That means it everywhere has a well-defined pressure and temperature and velocity, though I've omitted that in the following remarks. But those are not constant, so it's not globally in equilibrium. The system being isolated undergoes unitary evolution with a Hamiltonian H. The density matrix transforms to e to the minus IHT times itself times e to the IHT. Such a unitary transformation does not change the eigenvalues of the density matrix, so it does not change the von Neumann entropy. Now consider the thermodynamic entropy. Initially, simple measurements could have revealed the pressure P and temperature T as a function of position in the box. And assuming that's all we can learn from simple measurements, we'd define the thermodynamic entropy correspondingly. So we'd have an entropy density that's a function of the local pressure and temperature. We'd integrate it, and that would be what we'd call the thermal entropy. After a while, the fluid thermalizes, so P and T become constant, and simple measurements would reveal basically only the average temperature and pressure. The thermodynamic entropy will have increased because of coarse graining over microscopic information that we effectively lose when the system thermalizes. Now to ask what kind of entropy is the generalized entropy of Bekenstein. In Bekenstein's interpretation, A over 4G represents a coarse graining over unobserved internal structure of the black hole. So we should interpret that term as thermodynamic entropy. And Bekenstein proposed a generalized second law. He didn't say that the generalized entropy was constant. He says it's always non-decreasing, as is appropriate for thermodynamic entropy. But is the generalized second law true? So first of all, remember the classical limit of the statement is the Hawking area theorem of classical general relativity. dA dt is non-negative. And I will sketch a proof later, but I'm not sure if it will be today or tomorrow. Now, whenever we're near a classical limit in which the black hole is absorbing matter, the generalized second law is true because GH bar is so small that if dA dt is non-zero classically, then the increase in this term overwhelms whatever happens to S out. So we made such an estimate last time. To challenge the generalized second law in a more interesting way, we can consider a stationary black hole such as a Schwarzschild black hole, such that classically dA dt is zero. We let the black hole interact with quantum fields, and we ask what happens to the generalized entropy. Well, what must we mean by the entropy outside if the generalized second law is to be true? And what must we mean by it if the generalized second law is going to be interesting? Well, if the quantum fields are in a state such that the thermodynamic entropy makes sense, we'll be back in a situation in which the generalized second law is easily satisfied. The challenge is to ask if the generalized second law is true for an arbitrary state of the quantum fields outside the black hole. So in this generality, the notion of S out that makes sense is the microscopic or fine-grained entropy of the density matrix rho out that describes the quantum fields outside the horizon. So this is what we're going to mean by S out. So I've already explained one reason this is a good definition. Susskind and Uglum showed that with this definition, the generalized entropy actually makes sense, despite quantum corrections. But we want to ask whether it's true, whether the generalized second law is true. Now, two of you 2 days ago asked us basically versions of the same question, which is when a black hole is emitting Hawking radiation, so its area goes down, is the generalized second law satisfied? So before we do anything fancy, let's consider that special case. a black hole is all alone in empty space, it's emitting Hawking radiation. Is the generalized second law satisfied? Well, the answer is that S-gen is increasing. For a black hole to emit Hawking radiation at temperature T Hawking into the vacuum, which has temperature T equals 0, is a thermodynamically irreversible process that increases the entropy. I want to describe that explicitly, however. A careful estimate was made by Don Page in the 70s. I'll make a simple estimate ignoring what are called gray body factors. We consider a time delta t during which the black hole emits thermal radiation that fills a shell of thickness c times delta tau and c times delta tau. So here's the picture. The radiation, the black hole is this black blob in the center. During a time delta tau, it emits outgoing radiation that fills a certain shell, whose thickness is delta tau, and how far it is from the black hole depends on how far in the past from when we look at it was the time interval delta tau that we're talking about. Let n be the effective number of partial waves in which the outgoing radiation is emitted. There's something I didn't explain last time, which is that there's an angular momentum barrier because of which Hawking radiation is only emitted in modes whose angular momentum is not too high. And treating that carefully was what Don Page did in the 70s. But I'll just say that effectively the shell contains n modes of 1 + 1 dimensional massless outgoing fields at temperature T Hawking. And as you may know from your study of quantum statistical mechanics, for n massless right-moving fields, or in this case outgoing, but equivalently right-moving fields in one space, one time dimension, the entropy at temperature TH is given by this formula, and the energy is given by this formula. So the changes, see, if you compare these formulas, you'll see that the energy of thermal radiation in 1 + 1 dimension is the temperature over 2 times the radiation. Comparing the formulas, there's an extra factor of T Hawking, but there's also an extra 1/2. So the change in the energy and entropy of the radiation during time delta tau are related by delta E of the radiation is 1/2 of T Hawking times delta S. Or in other words, delta S is 2 over T Hawking times delta E. And as you'll see in a moment, that factor of 2 is very important. Conservation of energy says that the energy gained by the radiation is the energy lost by the black hole during the same time interval. So delta E of the radiation is minus delta E of the black hole. The black hole is emitting radiation adiabatically, so the change in its energy and entropy are related by dE equals TdS. Or in other words, delta E of the black hole is T Hawking times delta S of the black hole, or delta S of the black hole is 1 over T Hawking times delta E of the black hole. There's no factor of 2. If I compare this to the radiation where there was a factor of 2, and I remember that delta E of the black hole is just minus delta E of the radiation, you see that delta S of the radiation is minus 2 times delta S of the black hole. In other words, the energy gain of the radiation is twice the entropy gain of the radiation is twice the entropy loss of the black hole, reflecting the fact that for a body to radiate at temperature T Hawking into the vacuum at temperature 0 is thermodynamically irreversible. So that was a reality check, which actually, as I said, 2 of you asked about 2 days ago, showing that the generalized second law in this quantum domain makes sense. So that's encouraging, but can we give a completely general proof of the generalized second law for a stationary black hole interacting with quantum fields in an arbitrary state? Yes, as shown by Aaron Wool in 2011, provided we interpret S out as the von Neumann entropy of the density matrix of the quantum fields outside the horizon. So in Aaron's proof, you use the same density matrix that was, in Aaron's proof, you use the same relative entropy that was important in the proof of the Bekenstein bound. But we need to use one So it's defined the same way as before. Trace rho log rho minus rho log sigma. The key to the Bekenstein bound was the simple fact that the relative entropy is non-negative with equality only if rho equals sigma. For the generalized second law, the key is a deeper property, which is closely related to strong subadditivity of von Neumann entropy. So let U and V be two regions of space. V is contained inside U, as I've drawn. Let rho U and sigma U be the density matrices of two states of a quantum field for observations in region U, and let rho V and sigma V be the density matrices of the same two states in region V. Then the relative entropy between rho and sigma in region V is less than it is between the same two states in region U. Now, my version of the proof, I actually presented it at some summer school lectures a few years ago at PITP at the Institute in Princeton. And you can find it in section 3 of my lecture notes. If you want to understand why this is true, I mean, there are all kinds of places where you could find it. I think that for quantum field theorists, the way I explained it there is quite accessible. So you might want to look there. I'd love to explain the proof, but it would have taken at least half a lecture. And there simply were too many things I wanted to explain. So I reluctantly decided I couldn't. So we're going to need to use this very fundamental fact about relative entropies that basically goes back to Lieb and Ruskay and has had many proofs over the years. Now, what are the regions U and V we're going to consider? So I've drawn again the Penrose diagram for a black hole. And now I've drawn a space-like surface U that goes from the horizon to spatial infinity. So it's a partial Cauchy surface. It's not a complete Cauchy surface because it doesn't continue beyond the horizon. It's a partial Cauchy surface. And U will be the spatial region, or the space-time region will be its domain of dependence. For a smaller region, we'll take a later cut. So we'll cut the horizon at a later time, and we'll take a similar space-like surface from a later cut of the horizon. We'll cut the horizon at some later time and take a spatial surface, space-like surface, connecting that to spatial infinity. So in what sense does the later cut correspond to a smaller region for the sake of this monotonicity of relative entropy? Well, I'll explain two ways to look at it. One answer is that whenever we talk about a Cauchy surface or a partial Cauchy surface, observations on that surface are the same as observations on its domain of dependence, the space-time region where you can predict all the physics from initial data on U. So in this case, initial data on U will enable us to determine all the physics in the green region. We can't determine what's behind the horizon because we need initial data on a surface that would continue beyond the horizon. So something here could have come from down there, for example, beyond region U. And similarly, something down here, well, you see, it could go behind the horizon and never reach region U. So the green region is the region with the property that any particle traveling slower than light in the green region has to pass through region U. So it can be known from a knowledge of initial conditions on this partial surface U. Here's the similar domain of dependence for the later cut V. And one sense in which V corresponds to a smaller region is that its domain of dependence is simply a smaller portion of space-time. There's another way to look at it which will be technically useful. Instead of describing this region, the green region, using this partial Cauchy surface, we could use a different one, which would go like this. We could take U to be the horizon to the future of the cut, together with future infinity. And you can see that the space-time region, where you could predict everything from a knowledge of what there is here, is exactly the same as before, because anything in this wedge will traveling slower than light will end up passing through either this part of the horizon or else future infinity. So if you know what there is on future infinity in this part of the horizon, you'd know the physics in the whole green wedge. So I can replace U by this initial value surface. And similarly, you see, I can replace V by this initial value surface. And now you see the later cut of the horizon is just naively a smaller initial value surface. So we can apply the notion of monotonicity of relative entropy in this context. So this makes it obvious that we can use this inequality, the Lie-Bruschi, essentially inequality of monotonicity of relative entropy, in this situation. Now, rather as in discussing the Bekenstein bound, we expand the relative entropy as a sum of two terms. Well, okay, here for the moment I'm more naive. Trace rho log rho is minus S of rho, and I'll simply call minus trace of rho log sigma E. And we're going to study this inequality for two states. Rho will be the density matrix of the quantum state where we're trying to prove the generalized second law. And sigma will be another convenient state that we'll find. So that means that S of rho is going to be S out by definition. And therefore, the generalized second law will say that S out in region V minus E in region V, which is minus the relative entropy, should be bigger than S out in region U minus E in region U. Well, what we want is that the change in the area over 4GH bar plus the change in S out is non-negative. That's the generalized second law. So the change in S out is S out in region V minus S out in region U. And the change in the area is A in region V minus A in region U. So you see the inequality that we get for free from monotonicity of relative entropy will agree with the generalized second law if we can pick sigma so that with the help of Einstein's equations, EU minus EV is minus delta A over 4GH bar. So all we need is that Einstein's equation should give us this miraculous result here that we need to turn monotonicity of relative entropy into the generalized second law. Well, to proceed, we need to understand something about quantum fields on a null plane. So we'll start with Minkowski space. And I'll pick light cone coordinates. So I'll write the Minkowski metric as minus du dv plus dx squared, where the x's are transverse coordinates. And I let n be the null plane where u is 0. And then I cut n at v equals 0. So I've tried to draw this, although I'm not much of an artist, I'm afraid. So I've drawn the plane u equals 0. There are some normal coordinates, the x's. So I've drawn one normal coordinate. It runs from left to right. And then v runs this way. And the plane is slanted. That's supposed to make you think that it's a null plane. And then I cut it at v equals 0. So the green region where we make observations is to the future of v equals 0. So where v is positive, that's the green region. Now, the domain of dependence of the portion n plus of n above the cut is above 2 dimensions at Rindler space. That's because, you see, any particle in the Rindler wedge that's traveling slower than light will have to pass through the positive v part. So in this two-dimensional picture, I've suppressed the transverse coordinates. I've only drawn v and u. So n has been compressed to a line u equals 0. And I could have taken negative u and made this Rindler wedge drawn in green. I claim that anything in the Rindler wedge will have to pass through this green region by causality. If a particle is traveling slower than light, it has to travel through, simply because it goes slower than light, it can't escape passing through this null plane. But even if it's moving at the speed of light, unless it's moving exactly parallel to the null plane, which means it's precisely moving in in this direction, parallel to that null ray. Its transverse, as long as it has some transverse velocity, its velocity just in these two directions is less than light. It will again pass through that null cut. So, see, there's a set of measure 0. Okay. The wave function at a point has no content in quantum mechanics. Throwing away a point doesn't matter for a quantum mechanical wave function, which is really an L2 function. So we can assume everything above 2 dimensions, where we can assume that there's some transverse velocity. Everything passes through this half line, or this half plane that corresponds to this green region. So suppose we're only able to make observations along n above the cut, or equivalently in the right Rindler space. We learned last time that the density matrix that describes such observations in the vacuum state omega is the exponential of -2 pi k, where k is the Lorentz boost generator. And so far, I always wrote the Lorentz boost generator as an integral over time 0. But precisely because we can also use this upper part of the Rindler wedge as an initial value surface, we can alternatively write the Lorentz boost generator as an integral just on that surface. So here's a formula for the Lorentz boost generator. It's the integral over v from 0 to infinity, the integral over the normal coordinates, and then there's v times tvv, and we integrate from 0 to infinity because we only want the boost generator in half of the null plane. So this is a partial Lorentz boost generator that boosts fields in the right Rindler wedge, does nothing in the left Rindler wedge, and does something complicated in the future and past wedges. Now we want to generalize this for a general cut of the null plane of the form v equals f of x for an arbitrary function f of the normal coordinates. So now I've drawn the curve v equals f of x. Again, I've only drawn one of the x's to make it drawable. And the green region is now to the future of v equals f of x. Now let n plus comma f be the region of n, the region of the null plane, where v is no less than f of x. The domain of dependence of n plus f in spacetime is a wiggly generalization of the Rindler region. And I'm not a good enough artist to try to draw it, so I won't offer a picture. But we want to find the density matrix that describes measurements in n plus f, or equivalently in its domain of dependence. For that, we'll use the symmetries of operators on the null plane. First, we consider the operator p that generates translations in v. So here, I've just taken the null momentum, the generator of constant shifts of v is p. It annihilates the vacuum because all components of the momentum annihilate the vacuum. It's strictly positive on all other states because it's a null component of the momentum. It generates translations of operators on the null plane, of course, of all other operators too. So in particular, if you conjugate an operator by e to the IFP with constant f, that'll shift v by the constant f. Now, instead of a shift by constant f, take the operator p sub f, which is defined the same way, but with a non-constant function f that only depends on the normal coordinates. We're going to use this operator to map the cut at v equals 0 to the wiggly cut. Pf is not a symmetry operator, it doesn't commute with Hamiltonian, and off of the null plane, it probably does very complicated things. But on the null plane, it's simple. First, the null translation p and the Lorentz boost k have simple commutators with p sub f. So p sub f commutes with the null momentum, and the null Lorentz boost generator doesn't do anything to the normal coordinates, so this weighting by f of x doesn't matter. So it just rescales p sub f. These facts imply that p sub f annihilates the vacuum. You see, the vacuum is the unique state of p equals 0, and since pf commutes with p, it maps the vacuum to another state of p equals 0. And the eigenvalue can't be non-zero because of Lorentz invariance. So therefore P sub f has to annihilate the vacuum. Now, the key point is that e to the IPF conjugates operators on the region n plus of the null cut above the v equals 0 cut to operators on the region n plus f above the wiggly cut, the v equals f cut. If pf, to explain that, I'll point out the following. Suppose that f is constant. Well, then pf is just f times p, and we have the same formula as before. Now, if f isn't constant, what's different is that there are additional terms that involve derivatives of f. But each term involving the derivative of f involves a local operator of lower dimension than O. I wish I'd written this more carefully. O sub I is at the same point v plus f and x as O. So when you do this computation, you get a series of operators of lower and lower dimension, but all living at the same space-time points. And they have decreasing dimension, so the series stops after finitely many terms. Assuming the operator has finite dimension, O has finite dimension, it's a finite series, since after finite many steps, we'd be getting operators of negative dimension. So the important point is that conjugation by e to the IPF maps observables in the half null plane n plus to observables in the above the cut region n plus f. So we've learned two things. The operator e to the IPF leaves the vacuum state invariant, and conjugating by it is an isomorphism between the algebra of observables in region n plus and the similar algebra in region n plus f. So conjugation by e to the IPF will transform the density matrix sigma naught equals e to the minus 2 pi k for observations in region n plus to the density matrix sigma f for observations in the wiggly region. See, since you leave the vacuum state alone, so both of these density matrices are for observations in the vacuum. Since e to the IPF leaves the vacuum invariant, when you conjugate with e to the IPF, you just map one region to the other, leaving the vacuum alone. So you map one density matrix to the other. But we have the logarithm of sigma 0. And this, since we also know the commutator with P sub f, that gives us a formula for sigma f. Sigma f is this log sigma f is the same as log sigma 0, except v is replaced by v minus f. And I'll simply define that to be minus 2 pi times kf. So a small generalization of this formula, plus some discussion of Einstein's equations, will lead to the generalized second law. But before going there, I want to explain a heuristic explanation that's due to Wall. The idea is that there are no causal relations between operators on different null lines on the null plane, because they're space-like separated. So the null plane contains all these null lines that go in the v direction. Through any point, you can draw a null line in the null plane, and they're space-like separated from each other. And they can, since they're space-like separated, operators on different null lines commute. As far as the construction of its Hilbert space is concerned, the theory of the null plane is like an infinite tensor product of 1 plus 1 dimensional theories parameterized by x. In each of these theories at any given x, f is just a constant, and e to the IPF is a symmetry operator that conjugates the density matrix by v to v plus f, mapping k to k plus kf, mapping k to k sub f. So then we get the log sigma f by integrating the resulting formula over x. I wrote it as over kf, but over x. Now, as Wall explains, if it's possible to make a lattice regularization of the theory in the x directions while maintaining 1 plus 1 dimensional Poincare invariance, then this argument becomes rigorous. If you laticize the normal directions, then at each lattice point, you just have a 1 plus 1 dimensional theory. And for that value of x, f is just a constant. And the result we're claiming when f is constant is just the result we proved 2 days ago. So we have this very important formula for the logarithm of the density matrix above a wiggly cut. So now we need a little discussion of Einstein's equations, and then we'll get the generalized second law. So the black hole horizon is, first of all, a null surface. So it's swept out by light-like geodesics that are called horizon generators. So the reason for that is that if you're just outside the horizon, a light ray can escape. But if you're in the horizon, a light ray can't quite escape. It hugs the horizon instead and never escapes from the horizon. And those orbits of those light rays that are stuck in the horizon forever are null geodesics that are inside the horizon. So because there is such a null geodesic through every point on the horizon, the general form of the horizon metric is the following. It's GAB of x and v. It's some metric in A and B, but it's 0 times dv squared and 0 times dv dx. Where I've chosen to parameterize what are called the horizon generators, the orbits of light rays that are trapped in the horizon, by v at fixed values of the normal coordinates x. We can be a little more precise and ask that v should be an affine parameter along each null geodesic. The metric GAB of x and v is not arbitrary, but must obey a constraint equation, which is the null analog of the Ricciardori equation. So the constraint equation, see, Einstein equations are tensor equations. At each point in space, 10 equations. 9 of them depend on derivatives in the u direction. Only one of the 10 Einstein equations is a constraint that only involves the initial data in the null plane. And that's the VV component of Einstein's equations. The GVV, or equivalently RVV, the Ricci tensor, is 8 pi g times TVV. So to analyze this equation, it's convenient to set A to be the square root of the determinant of G, and theta to be A inverse dVA. This is a bold A. I think I'll have an unbolded A in a little bit. And then the Einstein-Ricciardori-Sachs constraint equation takes this form, where theta, the notation sigma is standard. Sigma is the traceless part of dV of GAB. So, well, I'm going to give a very brief sketch of something that's explained in much more detail. Actually, well, in many places, there's the famous textbook by Wald. I also wrote lecture notes on causal properties of general relativity, where you can read a very patient explanation of these things, which I tried to make as simple as possible. Now, before applying this constraint equation to the generalized second law, I'm going to briefly explain how it leads to the Hawking area theorem, which is the classical limit of the generalized second law. So we're just going to basically do what Hawking did and use the Einstein-Ricciardori-Sachs constraint equation to deduce the Hawking area theorem. So the point is that everything on the right-hand side is negative. Now, if these two terms were 0, you could just easily solve the equation. And when you solve it, you learn that if theta is negative, it goes to minus infinity at finite v. And you can show that that's a contradiction. That point is not completely trivial, and I won't, unfortunately, be able to explain it today. It's explained in Wald's book, and well, on that particular point, the explanation in my lecture notes is the same as the one in Wald's book. But remembering the definition of theta in terms of the derivative of the square root of determinant G along the horizon, you'd be suspicious of theta going to minus infinity. And you can actually show it can't go to minus infinity. So since this would happen to us if theta was ever negative along the horizon, it must be everywhere non-negative along the horizon. But since theta was defined as A inverse dVA, non-negative theta means that dVA is non-negative. But remember, A was just the square root of the determinant of the metric in the transverse directions, x. So the black hole area, the horizon area, is just the integral of A over the d minus 2 normal coordinates, 2 of them in 4 dimensions. So dv of little a being non-negative means the area is everywhere increasing. That's the Hawking area theorem. Now, in our study of the generalized second law, we want to consider a horizon that classically has constant area and study the quantum effects. Well, how do we make the area constant? Well, first, theta had better be 0, because if we prove theta can't be negative, and if it's positive, the area is increasing. So we assume theta is identically 0. But for this to be true, even as v increases into the future, the constraint equation tells us we need tvv in the classical to be 0 in the classical limit, and also sigma ab has to be 0. But theta and sigma ab being 0 tells us that the horizon metric is independent of v. So the case where the generalized second law is interesting is what's called a stationary horizon. The horizon in the classical limit is independent of the null time v. And therefore, the horizon metric just looks like this. Now we want to turn on effects of order h bar. So in the constraint equation, we need to consider effects of order h bar in tvv. So we're in a situation where tvv was 0 classically, but quantum mechanically it's of order h bar. On the right-hand side, since we're considering a situation in which theta and sigma are 0 classically, they're of order h bar, and those terms in the equation are of order h bar squared. Since a is constant classically, its derivative and its second derivative are of order h bar. So the derivative of theta was defined as a inverse dva. But in order h bar, since dva is already of order h bar, I can pull this one past the derivative. And dv theta is a inverse dv squared a plus order h bar squared. And theta squared is order h bar squared. Well, the term that survives in order h bar is minus 8 pi g times the expectation value of tvv times the classical a. In other words, in dv of theta, after pulling out a, I can replace this a by the classical a, because this term is already proportional to h bar, so I don't need a quantum correction here. And then I move a inverse to the right-hand side and replace it by the classical a. So the constraint equation in order h bar turns into this. And you see, that equation is just linear in a h bar. It only depends, it just tells you the second derivative of a h bar with respect to time as some explicit function if you know the quantum state. So we can explicitly solve it. And this is the solution with sensible behavior for v going to infinity, where I drop a possible additive constant that won't be important. Now I integrate over the transverse coordinates. And you see, the order h bar correction to the area is just the integral of a h bar. Little a is the area density, so little a h bar is the order h bar correction to the area density. And if I want to know the integrated area, the order h bar correction to the integrated area, I have to integrate this one over the horizon. But if I want to know the area at v equals f of x, that means I want to evaluate this at v equals f of x. So I do the integral for v prime bigger than f of x. So from this formula here, this one, we learned that this is the order h bar correction to the area. So the order h bar correction to the black hole entropy A over 4G is just minus 2 pi times this nice integral to the future of the cut. Now suppose there's a state whose density matrix sigma f in the region to the future of the cut satisfies log sigma f is minus 2 pi times this integral here that we just ran into. We'll find that state in a moment. Then the order h bar correction to the black hole entropy measured on the cut is just, well, sorry. The correction to the area is the expectation value in some state of this integral. But if that state happens to be log sigma for some other state sigma, then that means the correction to the area is the trace of rho log sigma, rho sub f log sigma f, where rho sub f is the density matrix of the state we're actually interested in, and sigma f is the density matrix of the magic state, whose density matrix obeys this. So rho, or rho sub f, is the density matrix in n plus f for the state we actually want, and sigma is introduced for convenience because of the nice formula for log sigma f. So if such a sigma f exists, then the relative entropy between rho f and sigma f, which is defined by this formula, is minus the entropy of sigma f minus this explicit correction, which is the order h bar correction to the area on the cut at f. So suppose we have two cuts G and F with G to the future of F. So this is a different picture of the horizon. I've made V run vertically. See, usually we think of a stationary black hole as sitting there. So on the Penrose diagram, it looks like the horizon is exploding outward at the speed of light. That's expressing the ideas that a massless particle in the horizon can't escape. But another intuitive picture is that the black hole sits there. And in keeping with that picture, I've drawn a stationary horizon, which has got some spatial configuration, and then it's independent of V. There are two cuts, G and F. G is to the future of F. So monotonicity of relative entropy says that the relative entropy between rho F and sigma F, between two states sigma and rho, on the cut F is bigger than what it is on the state G, on the cut G. And that's the generalized second law. I'm not sure if I should say any more because I've run over too much. I think I should explain the rest of the argument more patiently next time. So what I saw, okay, next time I'm going to review the last few steps of this argument because I think I went through it too quickly. But then there was one gap in what I've told you, which is that we didn't find the magic state sigma f, which is going to lead to this magical equality. We need a quantum state such that its density matrix sigma f to the future of any cut has this logarithm. And what that formula is good for is that when we solved Einstein's equations, we got a formula for the change in the area along a cut in order h bar. And if there is a state whose density matrix is this, then the area change can be written as the trace of rho log sigma for density matrices to the future of the cut f. And that's the last step in proving the generalized second law. So next time I will start by going over these steps more carefully, the ones I'm afraid I raced through a little bit too much here. And then I'll explain why there is a state sigma f and what is the state that has the right density matrix to complete the argument. So that will complete our discussion of the generalized second law. It'll take the beginning of the next lecture. And after that, what I will do next time is I'll go on to the Ryu-Takanagi formula and some of its consequences, where we have the microscopic von Neumann entropy rather than the thermodynamic entropy expressed as an area in gravity. But I think we'll stop here, promising to review a little bit what we said at the end and finish the argument next time. Thank you.
Thank you. So questions, comments? Can I actually ask you some notational question?
Yes, please.
TVV is an ingoing flux or outgoing flux? I was a little bit confused by the null coordinate.
Either one. Oh, well. Oh, sorry. Okay. I see what you mean. Sorry. Okay. It measures incoming flux.
Incoming flux, yeah. Yeah. And there was, I think, was a typo. I mean, this metric near the horizon you displayed several slides ago.
Yeah.
Should there be dV dx component?
No, that's very important. Let's go over that. There is dV du, but I set u equals 0, so I didn't write the dV du. This is only the metric on the horizon.
Oh, I see. Your x is not the radial. X is just the angular coordinate. Okay.
Yes.
Thank you.
I'm sorry if I didn't make that clear.
Yeah, I mean, I realized that. Thank you.
Yeah.
Yes.
The black hole horizon is a null surface.
Right.
So there's another coordinate u that's been set to 0 here. So there would have been a du dv term in the metric times some function of x, which I've omitted. And there might also be things like du dx and so on.
Right.
But there definitely is a du dv because the whole metric has to be non-degenerate.
That's true.
But the horizon is a null surface. It's extremely important that the horizon is a null surface. Again, that's something I would have wanted to explain in these lectures, but there just isn't time.
Right. Yeah, I was confused. X contains the radial part, so I was thinking of bidiametry actually. Sorry.
Well,
Yeah.
This is only the metric of the horizon. And then we showed that in this situation where the generalized second law is interesting, GAB is actually independent of V. So that this is just a spatial metric with no dependence on V plus 0 times the terms that involve V.
Mm-hmm.
Any other questions?
You can speak out if you like.
I would like to ask a question.
Jonggi? Oh, is it? Who was it? Sorry.
Dongso.
Oh, Dongso. Sorry.
Thank you very much for the nice lecture. Well, I mean, just a little clarification about the cut. So the cut is determined by, basically by the dynamical evolution of the black hole. Is that?
No. The cut is completely arbitrary. The generalized second, what does the generalized second law say? We can define the generalized entropy for any cut. It's defined by the same formula. The von Neumann entropy to the future, sorry. The generalized entropy is the area of the cut over 4G plus the outside entropy. So the generalized entropy is defined for any cut. And the generalized second law says that if we have two cuts, G and F, where G is to the future of F, then the generalized entropy on the cut G is at least as big as the generalized entropy on the cut F. So there's no dynamics in the choice of the cut. We pick the cut. And
I see.
No matter what cuts we pick, the generalized entropy increases toward the future. That's the meaning of the generalized second law.
Okay, thanks a lot.
You're welcome. I'm slightly worried I've made this, well, I don't know if I've made this argument as understandable as I hope to make it. When I was explaining it, it seemed like a lot to explain. When I was writing the slides, it seemed simpler. But I think it's an extremely beautiful fact, incredibly beautiful, that Einstein's equations, together with the monotonicity of relative entropy, magically, well, and some other facts, one of which I didn't quite finish explaining, which is the existence of a state where the density matrix sigma f was what I claimed. Everything fits together beautifully to give this generalized second law. So if we go back to where I first described it, with the first place I introduced the cuts. Here I had two different cuts. V is to the future of u. And I want to claim that the generalized entropy on the cut V is no less than it is on the cut U. Almost always bigger, but anyway, no less. Okay. Any other questions?
Junggi has a question.
Yes. Yeah, I have a question on this sigma f, some very special states.
Yes.
And you define there exists, you said there exists such states, and
Yeah.
that statement is some kind of exact statement, or it could be like some kind of approximation, like as you said, the density states need not to be exactly thermal, or in this case also some.
I'll tell you what the state is. With another 5 or 8 minutes, I would have explained it, but I was worried I was just going on too long. So I didn't finish the last step in the argument. To be honest, it's tempting to just explain it now, but probably I should
Yeah,
resist.
why not?
If that's your judgment, then I will.
Yeah, please.
But I think I will anyway begin next time by going over this argument again, because it's an extremely important argument. So to finish the argument, for a general stationary horizon, whose metric only depends on the x's and not v's, we need to find a state sigma such that for any region n plus f, where v is, for any cut, any region where v is bigger than f of x, the reduced density matrix has to be given by this formula, the unique formula that lets us finish the argument. Well, we did this in the case of that the horizon is a Rindler horizon in Minkowski space. Remember, we considered a Rindler wedge, and then there was the null plane parameterized by v with u equals 0. We took an arbitrary cut, v equals f of x, and we considered the density matrix to the future of that cut. And we got this formula. That was the density matrix for the vacuum. So for a Rindler horizon, if you take the state to be the vacuum, it has the density matrix we needed to finish the argument. Now we need to give the argument for the general case. Although physically, we're only assuming the horizon metric takes this form sufficiently far in the future, in the region where we're trying to prove the generalized second law. We can imagine a space-time in which the metric on some null surface has that form at all times. In fact, let H be a cut. We take our stationary horizon and consider a cut. Regardless of F, the metric on H is some spatial metric. In our black hole problem, we have some spatial metric. I think this sentence is maybe unnecessarily mysterious. I'm just saying, consider the d minus 2-dimensional spatial metric of any cut of the black hole in the region where we're studying it. Now take 2-dimensional Minkowski space times H. This is an auxiliary problem. We take the metric to be the 2-dimensional Lorentz metric plus this arbitrary d minus 2 metric. And we let n be the null surface u equals 0 in this space-time. And whatever quantum field theory we're studying in the field of the black hole, we can study the same quantum field theory in this space-time. We let omega be its ground state in this space-time. So when we were doing the Rindler horizons, we were in Minkowski space. So we had the R11 factor, but H was just RD minus 2. And we had d-dimensional Poincare symmetry. But the argument only used 2-dimensional Poincare symmetry. And R11 times anything has 2-dimensional Poincare symmetry. So we can repeat the whole discussion and argue that if we take the vacuum state, not in Minkowski space, but in R11 times H, then the reduced density matrix of the vacuum to the future of a cut satisfies the same formula that we had in Rindler space. Namely, log sigma f is minus 2 pi times all this. So
Then is it unique, or like this is one way to find some state that satisfy this equation, but could it be?
I expect it's unique, assuming the vacuum is unique. Our quantum field theory might not have had a unique vacuum. So you might have different choices. But I expect, I don't know a regular proof, I don't think, or at least not one I can remember offhand. But I expect that any state which satisfies this crazy condition we need for an arbitrary cut comes from taking the vacuum in R11 times H and restricting it to the future of a cut. I want to stress that R11 times H isn't in our spacetime. Our spacetime has a horizon, which looks like a piece of a Rindler horizon in R11 times H. But what we've done was to take the vacuum in R11 times H and deduce from it a density matrix, which has the property that if you restrict it to smaller regions along the horizon, you get the right things we want.
Okay, thank you very much.
Sure.
So, I mean, taking Rindler analogy, the vacuum you are imagining here is the usual Minkowski vacuum.
It's the standard vacuum of the theory on R11 times H. For example, if you're doing a Schwarzschild black hole, H is a sphere with a round metric.
Right.
So you take R11 times S2 in 4 dimensions. You
Right.
formulate your quantum field theory on R11 times S2.
Right.
And you take its vacuum state, whatever that is. It's not the same as the vacuum state in 4-dimensional Minkowski space. It's in a different spacetime.
No, but I mean, I was wondering, because once you have a horizon, of course, there are different choices like hot rocking, polar, and radiation vacuum. So, I mean, but I guess you are considering radiation vacuum.
This is not any of them for the physical spacetime. To explain what the state is, I went to this other spacetime, R11 times H. Then I construct the vacuum state. And then I constructed reduced density matrix to the future of some cut.
Okay.
Once I've done that, I could restrict it further to the future of a later cut. But I restrict it to some cut, the future of some cut. And then I observe the fact that the Rindler horizon in this spacetime has the same geometry as our stationary horizon of the actual black hole. So we can just borrow that state from the auxiliary spacetime and use it in the import it into the vacuum, import it into the black hole horizon. A density matrix is a function of fields on an initial value surface, pairs of fields. A quantum state would be a function of a field, but the density matrix is a function of a pair of fields on an initial value surface, which here we take to be the Rindler, the future of a cut of the Rindler horizon in this spacetime. Whatever that function of fields is, we literally use the same function of fields as a density matrix in the black hole spacetime. If your quantum field theory for which you're proving the generalized second law is a free field theory, you can make this completely explicit. Then you have an explicit description of the vacuum, and you can fairly explicitly describe its reduced density matrix in a region, semi-explicitly. And but anyway, it's given by a Gaussian formula with a kernel that's hard to compute explicitly, but you can describe the equations that determine it. And you use the same Gaussian kernel, same Gaussian density matrix on the black hole horizon. Oh, if you look at Aaron Wall's paper, he doesn't explain it exactly the way I did, I don't think. I thought this was a shortcut to explaining it, but I hope I haven't confused you. You literally take the vacuum state in R11 times H, whatever that is, like R11 times S2 maybe. you then consider it on a Rindler wedge in R1 1 times h. That means that u equals 0. And then you go above to the future of some cut. Well, okay. Roughly speaking, you simply use the vacuum state on R1 1 times h, and you import it to the black holes, to the black hole horizon.
I understand. So, any other questions, comments?
I have a question.
Okay,
Yes, go ahead.
one.
Yes, thank you. Does this generalized second law holds for cosmological horizon? Is there any proof?
I think the argument holds for any horizon, but let me try to think more carefully. Well, cosmological horizons usually aren't stationary, are they? Okay. Whatever the Hawking area theorem holds, I think you're going to find that there's a generalized second law.
Mhm.
I think the answer is yes. I'm slightly worried I'm forgetting something, but as far as I can see, it's correct. So for example, if you consider the cosmological horizon of an observer in de Sitter space, it's actually stationary. In other words, the metric of the horizon has exactly the form I said. It looks like this. Well, it looks like this with the further property that's independent of V. If it depends on V, then the Einstein-Ricciardori-Sachs constraint equation says that the area is increasing, and then the generalized second law is trivial. It has no more information than that. But for a de Sitter horizon, it's stationary. The metric of the horizon, cosmological horizon, is like this with no dependence on V. And then I believe exactly the same proof applies, as I think Aaron Wall probably even said in his paper.
Thank you very much.
Sure.
Okay, so again, we are pushing 11:30. So unless there is further question, maybe it's good time to close the session. Let's thank Edward again.
Thank you, and see hopefully most of you tomorrow night.
Yeah.